Welcome back to Chemical Kinetics. In our first lecture, we focused mostly on the molecular picture. We talked about collision theory, activation energy, reaction mechanisms, and catalysts, and we used those ideas to answer the question, why do reactions happen at different rates? Now we're going to take the next step. If I tell you that one reaction is faster than another, what does that actually mean? How do we measure fast? And once we measure it, can we develop a mathematical relationship that describes how different conditions affect that rate? That's what we're going to focus on in this lecture today. We'll start by defining reaction rate, then connect rate to stoichiometry, and finally introduce one of the major tools in kinetics, the rate law. There are several learning objectives listed here, but they really fit into one progression. First, we're going to learn how to measure a reaction rate. Then we'll learn how the stoichiometry of a reaction connects the rates of disappearance of reactants and appearance of products. From there, we'll introduce rate laws and reaction order and use experimental data to determine how concentration affects reaction rate. And finally, we'll reconnect all of that math to the reaction mechanisms we discussed in Lecture 1. As before, you'll see several places where I ask you to pause and work on your active homework. Please actually do that. This material is much easier to learn by doing a few problems at a time than by watching me talk about the calculations for 30 minutes and then trying them all afterward. Before we talk specifically about chemical reactions, let's think about the word rate. You already use rates all the time. If you're driving, your speed might be measured in miles per hour. Your heart rate describes the number of beats occurring over some period of time. In each case, we're looking at the change in one variable relative to the change in another variable. In chemistry, our variable of interest is usually concentration. So a reaction rate describes the change in concentration of a substance over the change in time. In a very general sense, that's all a reaction rate is, the change in concentration divided by the change in time. The details become more interesting, though, once we start asking which chemical species we're measuring. So let's start with the simplest possible reaction, where reactant A becomes product B. As the reaction occurs, A is being consumed, so the concentration of A decreases. At the same time, B is being produced, so the concentration of B increases. You can see that in the graph here. The reactant concentration drops over time while the product concentration rises. That means we could measure the progress of this reaction in two different ways. First, we could monitor the disappearance of A, which is going to be represented as minus delta A, or the change in A, over delta time, or the change in time. Or we could monitor the appearance of B as the change in B over change in time. Notice the negative sign associated with the reactant, and that's because the concentration of A is decreasing. Its change in concentration is negative, but when we report a reaction rate, we typically want to report the rate as a positive quantity. So for a reactant, we put a negative sign in front of the expression. Products are increasing, so their changes in concentration is already positive. Let's put some actual numbers to this. Continuing with the example reaction where A is converted to B, and we're monitoring the concentration of A over time, as you can see here, at 0 seconds, A is reported to be 0.8 molar. After 10 seconds, it's now 0.65 molar, and at 20 seconds, it's 0.52 molar, and at 30 seconds, it's 0.42 molar. So from this data, let's try calculating the average rate of disappearance of A between 10 and 20 seconds. Our expression is negative change in A divided by the change in time. So we take the final concentration, 0.52 molar, minus the initial concentration, 0.65 molar. So that sum is going to be the negative of 0.13 molar. Our time interval is 20 minus 10, or 10 seconds. So we have negative 0.13 molar divided by 10 seconds. The two negative signs cancel, giving us an average rate of 0.013 molar per second. And notice those units. Concentration divided by time gives us molarity per second. Now, before moving on, Look back at the table. Without doing the calculation, would you expect the average rate from 20 to 30 seconds to be greater than, less than, or about the same as the rate from 10 to 20 seconds? Think about that for a second. From 10 to 20 seconds, A decreases by 0.13 molar. But from 20 to 30 seconds, it decreases by only 0.10 molar over the same amount of time. So the reaction appears to be slowing down. And that's actually what we should expect. A reaction does not usually proceed at the same rate from the beginning to the end. Look at the graph here. Early in the reaction, the concentration curves are steep. Later, they begin to flatten out. The reaction is usually fastest near the beginning when reactant concentrations are highest. As reactants are consumed, their concentrations decrease. Think back to collision theory. Fewer reactant particles in the same volume means fewer opportunities for reactant particles to encounter one another. So the number of successful collisions decreases and the reaction rate therefore slows down. This also means that when we talk about an average rate, the answer depends on the particular time interval we're looking at. The average rate from 0 to 10 seconds may be very different from the average rate from 50 to 60 seconds. Later, we'll develop equations that allow us to describe this changing behavior more precisely. So let's stop here, though, and practice the basic idea of reaction rate. Return to your kinetics homework assignment in active and complete questions 10 and 11. Pay particular attention to whether you're looking at a reactant or a product and what that means for the sign of the concentration change. Pause the video here and come back when you're finished. Now, we're going to add one additional complication here. Let's consider the reaction where nitric oxide and oxygen react to form nitrogen dioxide. So here's my question. Do all three chemical species change concentration at the same numerical rate? Take a look at the graph. The answer is no. And the reason is something you're already very familiar with. Stoichiometry matters. For every one molecule of oxygen that reacts, 2 molecules of nitric oxide must react, and 2 molecules of nitrogen dioxide are going to be produced. So the concentrations of these substances cannot all change at the same numerical rate. Their changes are linked by the coefficients in the balanced chemical equation. Look more closely at our reaction. Because the coefficients tell us that 2 nitric oxides are consumed for every 1 oxygen molecule consumed, the concentration of nitric oxide decreases approximately twice as fast as the concentration of oxygen. Likewise, the 2 dioxide molecules, nitrogen dioxide molecules, are produced for every oxygen consumed. If we want to describe one consistent reaction rate, we need to normalize these differences. And we do that by dividing the rate of change of each substance by its stoichiometric coefficient. So for NO, we divide by 2. For oxygen, its coefficient is 1, so dividing by 1 doesn't visibly change anything. For NO2, we also divide by 2. And because NO and oxygen are reactants, their expressions receive negative signs, while NO2 is a product, so its expression is positive. Once we account for all of these coefficients, all 3 expressions describe the same overall reaction rate. We can generalize that idea for any reaction. The lowercase letters represent the stoichiometric coefficients. So for our reaction rate can therefore be written as -1 over the coefficient of molecule A times the change in A over time, which is equal to -1 over B times the change in molecule B over time, which is equal to 1 over C times the change in the concentration of molecule C over time, which is equal to 1 over D times the change in D over time, and there, so on and so forth. But don't get overwhelmed by the notation. The underlying idea here is straightforward. Stoichiometry normalizes the rates at which the different chemical species change. And this becomes useful in another way. If we know how quickly one species is disappearing or appearing, we can use the stoichiometric relationship to determine how quickly another species must be changing. It's really just stoichiometry applied to average rates. Let's work through an example using the same reaction as before. Suppose oxygen is disappearing at a rate of 0.2 molar per second. How quickly is NO2 being produced? Start by looking at the relevant pieces of our rate expression. The negative change in oxygen over time equals 1/2 of the change in NO2 over time. We're told that the oxygen concentration is decreasing by 0.2 molar per second. Because we're describing its disappearance, the reaction rate expression converts that to a positive 0.2 molar per second. Now, compare the stoichiometric coefficients. For every 1 oxygen consumed, 2 NO2 are going to be produced. So NO2 must appear twice as quickly. Multiplying 0.20 molar per second by 2 gives us 0.4 molar per second. So if oxygen is being consumed at 0.2 molar per second, NO2 is going to be produced at 0.4 molar per second. You can certainly solve these using the full rate expression, and I want you to understand that equation. But you can also use your chemical intuition here. Look at the balanced chemical reaction first. Ask yourself what the mole ratio tells you should happen. That can help you catch calculator mistakes, by the way. Okay, so now I want you to try several of these on your own. Work questions 12 through 19 in your active homework. There are several questions here intentionally because this is one of those skills that becomes much easier with repetition. Feel free to refer back to the previous slide while you're working. You're not taking an exam right now. You're learning, so use your notes, use the examples, and take your time. Pause here and come back when you're ready. Now we're going to shift from simply measuring reaction rate to figuring out what controls it mathematically. Think back to lecture 1. We said that increasing concentration generally increases the reaction rate because particles collide more frequently. That's a useful qualitative statement. But now we want something more precise. If I double the concentration, does the rate always double? Could it quadruple? Could it stay exactly the same? The answer is that all of those possibilities can occur depending on the reaction. The mathematical relationship between reactant concentration and reaction rate is described by what we call the rate law. For a reaction involving reactants A and B, a general rate law might look like this, where the rate is equal to lowercase k times the concentration of A raised to the m power times the concentration of B raised to the n power. Let's break down what each of these things mean. Again, the brackets you should recognize represent the molar concentrations of our species in the reaction. K, lowercase k, is what we call the rate constant, and the exponents m and n are called the reaction orders with respect to molecule A and B. Now, I want you to pay very close attention to the next statement because this is probably the single most important rule on this slide. These exponents are determined experimentally. You cannot normally look at the coefficients in a balanced overall chemical equation and use those coefficients as the exponents in the rate law. It's very tempting to do. Don't do it. Balanced equations tell us stoichiometric relationships. Rate laws tell us how concentration affects reaction rate. Those are different pieces of information. Later, we'll see one very specific situation where coefficients can be used directly, but for an overall reaction, assume that reaction order must come from the experimental evidence. Let's look more closely at the exponents. If our rate law is the rate is equal to k times A raised to the m times B raised to the n, then m is the order of the reaction with respect to A, n is the order with respect to B. And if we want to describe the overall reaction order, we add those two exponents together. So, for example, if our rate law is equal to the rate times k, rate is equal to k times the concentration of A, and we see no exponent there, so we can assume it's 1, the reaction therefore is first order with respect to A and first order overall because there is no other species. However, if we have a rate in which the rate is equal to k times A squared times B, then the reaction is second order with respect to A and first order with respect to B, and then we add those two exponents together, 2 plus 1, giving us third order overall. But reaction order tells us more than just how to classify the equation. It also tells us how sensitive the reaction rate is to the change in the concentration of these individual reactants. Let's make the exponents physically meaningful, okay? So suppose, again, we have rate is equal to K times the concentration of A raised to 1, or its first order. If we double the concentration of A, then A is multiplied by 2. 2 raised to the first power is 2. So the reaction rate, therefore, will also double. Now, suppose that the rate is equal to K times A squared. If we double A, now we're multiplying the rate by 2 raised to the 2, or 4. So in this case, doubling the concentration of A causes the reaction rate to quadruple. Now look at zero order reactions. If we have a zero order reaction, we would say that the rate is equal to K times A raised to the 0. Any non-zero number that's raised to the 0 power immediately becomes 1. So that means that the concentration term effectively disappears from the equation. So therefore, changing the concentration of A has no effect on the reaction rate when it is zero order. That's how the reaction order tells us how strongly the rate responds when a reactant concentration changes. Let's make sure that idea feels comfortable. Suppose we triple the concentration of a reactant. If the reaction is first order in that reactant, then we are saying 3 raised to the first power is equal to 3. So the reaction rate therefore triples. If the reaction is second order, then we would be saying 3 raised to the 2 is equal to 9. So the reaction rate becomes 9 times faster. If the reaction is zero order, that's the same thing as saying 3 raised to the 0, which is equal to 1, so the reaction rate does not change at all. This is a really useful way to think about reaction order. Rather than memorizing that first order means the exponent 1, think, how does changing the concentration change the rate? That's the experimental meaning of that exponent. Let's stop here so you can practice working with reaction orders and rate laws. Complete questions 20 through 27 now on your homework. As you're working, keep asking yourself, how did the concentration change, and what should that do to the rate based on the exponent? Pause the lecture and come back when you are finished. Now we need to tackle a really important question. How do we actually know the value of those reaction orders? Well, the only way we can figure them out is to measure them experimentally. Again, you cannot usually look at the balanced equation and determine the rate law. Instead, chemists conduct experiments in which the reactant concentrations are systemically changed and the resulting reaction rates are measured. Then we ask, when I change this concentration, what happened to the rate? These experimental evidences help us predict what are the exponents in the rate law. One common approach is called the method of initial rates. Here we have 3 experiments. In each experiment, the concentration of A and B are controlled, and the initial reaction rate is measured. The basic strategy is extremely important here. Compare experiments in which only one reactant concentration changes at a time. Let's first compare experiments 1 and 2. In these experiments, B stays constant, but A doubles. Now ask what happens to the rate. As you notice, the rate doubles. So if doubling A causes the rate to double, A must be raised to the first power. The reaction is then first order with respect to A. Now let's compare experiments 1 and 3. This time, A stays constant while B doubles. What happens to the rate now? It increases by a factor of 4. So we need an exponent such that 2 raised to the n equals 4. That exponent is 2. So the reaction, therefore, is second order with respect to B. This is why choosing the correct experiments to compare matters. We only want one variable changing at a time so we can isolate its effect. Now that we know our reaction orders, we can write the rate law. We determined that the reaction is first order in A and second order in B. So the rate is going to be equal to K times A times B squared. Once we know the rate law, we can also determine the rate constant, K. Here you're going to choose any of the experimental trials. Plug the measured rate and concentrations into the rate law, then solve algebraically for K. Using the values shown here gives us a rate constant of K is going to be equal to 50 inverse molar squared inverse second squared. Don't worry if those units look a little strange. The units of K change depending on the overall reaction order. The important thing right now is the process. First, use the experimental comparisons to determine the exponents. Second, write the rate law. Third, use one experimental trial then to solve for K. Once you know the rate law and the values of K, you can predict the rate under other concentration conditions. Here's a reference showing the units of K depending on the reaction order. Notice that the units of the reaction rate itself stays the same. It's always going to be molarity per second. But the units on the concentration terms in the rate law change depending on their exponent. So K has to carry whatever units are necessary to make the entire equation come out to molarity per second. For a zero order reaction, K has units of molarity per second. For first order, the units are inverse seconds. And then for second order, it's inverse molarity seconds. And for third order, it's inverse molarity squared seconds. I don't want you to treat this as a random table to memorize. You can derive the units of K from the rate law if you know the reaction order. But this table is a useful reference. Now you're going to practice the full process. Work questions 28 through 37 in your active homework. Use the previous example as your model. For each problem, slow yourself down and follow the same sequence. Compare experiments where only one concentration changes. Determine the order with respect to each reactant. Write the rate law, then solve for K if the problem asks. There are quite a few questions here, so take your time, pause the video, and return when you're ready. Now we're going to try to reconnect all of this math back to lecture 1. Remember that an overall chemical reaction may occur through a series of elementary steps. And earlier I gave you a very strong warning. Do not use coefficients from an overall balanced equation as exponents in the rate law. Now we finally get to the important exception. For an elementary reaction, the rate law can be written directly from the reacting particles in that elementary step. Why? Because an elementary step describes a single molecular event. So if an elementary step is 2 molecules of A react to produce product P, then 2 molecules of A must participate in that event. And the rate law for the elementary step, therefore, is going to be equal to the rate is equal to Ka squared. But this is the connection between molecularity and the rate law. But remember the qualifier here, elementary steps. Do not take this rule and blindly apply it to an overall balanced equation, which, if you remember, is made up of multiple steps. So let's make sure you can recognize that distinction. Return to the homework and complete questions 38 and 39. These focus specifically on writing rate laws for elementary steps. Pause here and come back when you're finished. Now think back to the bottleneck idea from lecture 1. In a multi-step reaction, one elementary step may be substantially slower than the others. That slow step is our rate determining step. Suppose our slow elementary step is A plus B react to make an intermediate. Because this is an elementary step involving one A and one B, its rate law would be the rate is equal to K times A times B. And because this is the slowest step, the bottleneck, it may control the rate of the overall reaction. Now we're beginning to see why reaction mechanisms aren't just theoretical stories about what molecules might be doing. We can test proposed mechanisms using experimental evidence. A reasonable mechanism must satisfy at least 2 things. First, when we add the elementary steps together, they need to produce the correct overall balanced reaction. Second, the mechanism needs to predict a rate law that agrees with the experimentally observed rate law. That's an important piece of scientific reasoning. We don't simply invent a mechanism that seems plausible. We ask whether that proposed molecular explanation is consistent with what we actually measure in the laboratory. So let's step back and look at the progression we've made in this lecture. We began with an experimental observation. We watch concentration change over time, and from that we can define a reaction rate. Then we investigate how changing concentration changes that rate. That gives us a rate law. The reaction orders in that rate law come from experimental evidence. And finally, reaction mechanisms give us a molecular level explanation for why we observe that particular rate law. So the progression is experimental observation, yields rate laws, yields mechanism. And notice how nicely this connects back to Lecture 1. Lecture 1 gave us the molecular picture, collisions, energy barriers, and reaction pathways. Lecture 2 has given us a way to quantitatively measure and describe what those molecular events produce. In our next lecture, we're going to ask a different question. Instead of asking how fast is the reaction happening, we're going to ask, if I know how fast it reacts, can I predict how much reactant will remain after a certain amount of time? That's where integrated rate laws and half-life come in. Make sure you've completed the assigned active questions before coming to class. We'll use our class time then to work more deeply with these relationships, troubleshoot the calculations, and connect the equations back to what is actually happening chemically. Until then, I hope you all have a great day. Bye.